You know, when you think about the history of programming, it's not this clean, straight line of one invention after another. It's actually way more interesting. It's this cycle, a 200-year-long chain reaction, where every time we solve one massive problem, we accidentally create the next one. So let's follow that chain, from pure logic all the way to AI.
Now, this whole journey is based on some fantastic work by Tony and Ara, who really laid out this entire evolution. Of course, we've put all the details and links to his work right down in the description if you want to go deeper. And really, this is the main idea we're going to keep coming back to. Every single breakthrough, every one, wasn't some final answer. Nope. It was just the starting gun for the next big race, the next big problem to solve. So let's kick this off with a pretty big question, one that's going to frame this whole story. What if programming was never actually about writing code? What if, this whole time, it's really been about one thing: trying to close that gap between what we think in our heads and what a machine can actually do? Okay, so to find the beginning, we have to go way back to a time before computers were even a thing. We're starting with Section 1, the theoretical dream. This is where programming wasn't hardware, it was just pure logic, an idea living in the minds of incredible mathematicians like Euler and Boole.
At the heart of it all is this one concept, the algorithm, just a formal set of rules to solve a problem. Now, this was a huge deal because it meant you could separate the act of reasoning from the physical world. But it was Ada Lovelace who saw the next step, who made that critical connection that these abstract rules could actually be run by a machine.
Listen to this quote. Lovelace's vision here is just mind-blowing. She didn't just see a fancy calculator. She saw a machine that could weave patterns with logic, the same way a loom weaves patterns with thread. She saw the creative soul of computation way, way before anyone else. So at the end of this first phase, they'd solved a huge problem. Logic could be written down, formalized into rules. But, of course, that created the next problem. It was all just theory on paper. There was no machine, no hardware that could actually run these things at any kind of useful speed. The challenge wasn't about logic anymore, it was now all about engineering.
And that engineering challenge, it drops us right into Section 2, programming with wires. Welcome to the hardware era. This is where people like Alan Turing brought theory crashing into the real world, and where changing the program literally meant changing the machine itself.
I just love this quote from Alan Turing. You can feel the sense of wonder and, honestly, the unpredictability of it all. These weren't just simple tools. They were these new, strange things that could spit out results their own creators didn't see coming.
Think about programming one of the first computers, the ENIAC. It was an incredibly physical, hands-on job. There was no software. You had these brilliant mathematicians, many of whom were women, who would spend their days plugging and unplugging hundreds of wires on these massive boards just to map out the logic. Changing a program wasn't about typing. It could take days of hard manual labor.
So boom, the problem of speed was solved. Calculations that would have taken months could now be done in seconds. But you see where this is going. This created a brand new problem. The programming bottleneck. The actual physical act of setting up the program was now taking way, way longer than the calculation itself.
That bottleneck is exactly what leads us to our next giant leap forward. Here in Section 3, the birth of code. This is the moment when John von Neumann comes along with a truly revolutionary idea. What if we could separate the instructions from the physical machine? And the breakthrough was called the stored program concept. For the very first time, the instructions, the software, could live in the exact same memory as the data. This meant you could change the program without ever touching a single wire. This right here, this is the moment code, as we think of it, was really born.
But this gave birth to a totally new language, machine code. And that string of characters you're looking at, that's not just random gibberish. It's a very precise, very direct instruction for the computer's processor. It's a language built for silicon, not for the human brain, which made it incredibly efficient for the machine, but an absolute nightmare for a person to read or write without making a ton of mistakes.
So, the physical bottleneck of rewiring, solved, gone. But it was immediately replaced by a mental one. Programmers were suddenly dealing with this extreme cognitive load, trying to memorize all these obscure codes, and naturally, that led to a whole lot of errors.
So what do you do when the cognitive load gets to be too much? Well, you make the language more human, and that brings us to Section 4, making code human-readable. This whole era was led by pioneers like Grace Hopper, who were dead set on translating that dense machine logic into something that felt a little closer to human language.
Grace Hopper's attitude is just perfectly captured right here. She completely rejected the idea that programmers had to be these wizards who could memorize cryptic machine codes. She was the one pushing for machine-independent languages that, normal people could actually learn.
And guess what? It totally worked. The accessibility problem was solved. All of a sudden, scientists, business users, they could all start writing their own programs. But what happens when everybody starts writing code? Well, the programs get bigger and a whole lot messier. This created the infamous problem of spaghetti code, just a tangled, unmanageable nightmare of instructions.
The solution to all that chaos came from Alan Kay, and it started with this beautiful analogy. He imagined software not as one giant list of instructions, but more like a collection of biological cells, these independent little objects that could only communicate with each other through simple messages. And that was the birth of object-oriented programming, or OOP.
The whole method was just brilliant. First, you create an object, say a window on your computer screen. Then, you hide all of its messy, complicated parts inside of it, and from then on, you just interact with it by sending it simple messages, like close yourself or resize. This was a game changer. It let massive teams build enormous software without constantly tripping over each other. So OOP solved the huge problems of scalability and organization, but in doing so, it created what you could call the expert gap. These new languages like C++ and Java, they were powerful, but they were also deeply abstract and complex. Programming once again became this highly specialized skill. You really needed a formal computer science degree to get in the door.
And that, finally, brings us to right now, to Section 5, the final barrier, intent. We are living through the next great shift, right this second. The one where we are finally teaching the machine to understand what we mean, not just what we meticulously type into a file.
And this says it all, doesn't it? On the left, you've got the old way, rigid, unforgiving syntax, where a single misplaced semicolon could ruin your whole day. And on the right, the new way, just telling the machine your goal in plain English. We're moving away from the language of syntax and into the language of intent.
So, here we are, after 200 years, you could argue we finally solved that great translation gap between human thought and machine logic. We can pretty much just speak our ideas into existence. But just like every other step in this story, solving that problem has created the next one. The big question for our time is no longer just how do we write the code, but how on earth do we trust and verify all this code that an AI is writing for us? And that's the next great challenge we all have to solve.